Okay, we're going to talk about differential equations. We're going to talk about slope fields. And eventually we're going to talk about Euler's method. So, turn to page 404. So on page 404, they give us some information to think about here. So let me just read and you think along with me. Much of this will seem familiar, but it's maybe the book says it in a little bit different way than I've said it to you in the past. So starting on page 404, a function y equals f of x is called a solution of a differential equation if the equation, meaning the differential equation, is satisfied when y and its derivatives are replaced by f of x and its derivatives. And what they didn't say, but they mean, well, they did too say it. They said is satisfied. An equation is satisfied when you do substitution and you get a true statement. Okay? So, replacing the original y with the y that is your solution and replacing an original y prime or f prime of x or dy dx or whatever they called the derivative with what you found to be the derivative. So when you replace the original y, the original derivative, with what you found to be the y and what you found to be the derivative and get a true statement, then what you found to be the y is called a solution of the differential equation. For example, differentiation and substitution would show that y equals e to the negative 2x is a solution of the differential equation y prime plus 2y equals 0. Now, I'm not going to do it all because they don't either, but that means that if I took that and put it in there for y, and then I found the derivative of what I have circled and put it in for y prime, I would get a true statement. That's what it means to be a solution. It can be shown that every solution of this particular differential equation is of the form y equals c e to the negative 2x, where c is any real number. When books, especially math books, say things like it can be shown, it means they're not going to show you right now, but it's fairly well established, yes, this is accurate, okay? Because sometimes the showing would distract you from the bigger point. This solution is called a general solution. We've used that, haven't we? When we had the c in there, we call those general solutions. Some differential equations have singular solutions that we've never talked about that cannot be written as special cases of the general solution. Uh-oh. However, such solutions are not considered in this text. Whew. The order of a differential equation is determined by the highest order derivative in the equation. For instance, y prime equals 4y is a first order differential equation. If we made that y prime equals 4y double prime, that'd be a second order differential equation. Okay? In section 4.1, you saw that the second order differential equation, s double prime of t equals negative 32, has the general solution, and then we've used this a few times, haven't we? Okay? That's our position function for a free fall. So s of t equals negative 16t squared plus c1t plus c2, which contains two arbitrary constants. It can be shown that a differential equation of order n has a general solution with n arbitrary constants. So in other words, a third order differential equation, its general solution would have three constants, three c's. If it was a seventh order differential equation, you'd have seven c's. Oh, the seven c's. Okay? Now, geometrically, the general solution of a first order differential equation represents a family of curves known as solution curves. And we have used slope fields to come up with a family of solution curves, haven't we? They'll give us a slope field. They'll tell us to make two of them one of which has to go through the given point, that kind of thing. For instance, one for each value assigned to the arbitrary constant. So look at up here at these. Every one of those graphs has a different C. Here's the differential equation. Here's the general solution. Here's what the graph looks like when C equals 1. Here's what it looks like. Oh, C equals 1 looks like that and that. Here's what it looks like when C equals 2, this and this. Here's what it looks like when C equals -1, here and here. And when C equals -2, looks like that. Okay? Different C's, different graphs. For instance, you can verify that every function of the form y equals C over x is the solution, or is a solution, of the differential equation xy prime plus y equals 0. All right, this figure shows 4 of the solution curves corresponding to different values of C. And it really is just 4, right, because that and that are considered one curve. It's the same function. It's just that graph is not continuous. Okay? As discussed in section 4.1, particular solutions of a differential equation are obtained from initial conditions that give the value of the dependent variable or one of its derivatives for a particular value of the independent variable. In other words, they give you a y for a particular x. They give you an ordered pair that will be a solution. They'll give you a point on the graph of the solution. Okay? The term initial condition stems from the fact that often in problems involving time, the value of the dependent variable or one of its derivatives is known at the initial time t equals 0. So even if it's not really a t equals 0, we still call it initial condition because they all just kind of got called initial conditions. Just like you'll call a Pepsi a Coke if that's what you call them. You know what I'm saying? They call them initial conditions, even if they're not t equals 0. For instance, the second order differential equation, s double prime of t equals -32, having this general solution, might have the following initial conditions. And if they do, then in this case, the initial conditions yield this particular solution because our position function for a free fall depends upon the position at the beginning of the free fall and the initial velocity. So that's why the initial conditions give you different particular solutions. Okay? Now, most of this, I think, was familiar to you. And considering that we've already done a lot of different, well, not a lot of differential equations, but we've solved several. We've dealt with slope fields quite often. And then now the book does this again, makes me think that they had one edition of the book, realized, uh-oh, all this stuff's being more emphasized by the AP people. We got to beef it up and have another section of this to make sure the students know this. So it's not that this is actually intended to be new information. I think it's intended for you to look at the same kind of information in a different way. Because the problems we're getting ready to do should be easier than the ones we've done, but I'm not sure that they are. Because what we're getting ready to do is they're going to give us solutions to differential equations and make us show that they really are solutions. Or they're going to give us a potential solution and ask us, is this really a solution? Whereas what we've done in the past is we started with the differential equation and we came up with the solution. So in theory, taking a solution and showing that it's the solution is a little easier. Like if it was algebra, you know, if you had x plus 2 equals 5 and they asked you, is x equals 3 a solution? In theory, that's easier than solving it for x yourself. So, but we've already solved for x itself. Now they're going to ask us that. Okay? So it's a different kind of problem. Ought to be easier. I'm not sure that it is, though. Kind of working backwards. So let's do a few examples. So turn on over to page 409. And let's begin with number 24. And I'm jumping all around in the examples we're going to do too, so bear with me. So for number 24, the directions say to determine whether the function is a solution of the differential equation, and then they give us the differential equation. It's xy prime minus 2y equals x cubed times e to the x. So when I write this down, it makes more sense to me to write down the differential equation first, which we'll shorten to DE. Guess what DE stands for? Differential equation. So write down your differential equation, your DE, and then they're asking us whether or not y equals x squared e to the x minus 5x squared is a solution. That's why I put a question mark right there. Okay? Now remember how they defined solution. A function is a solution if y and its derivatives can replace the original y and its derivatives and get a true statement. Okay? So we've got the original y. It's that. We're going to substitute that right there for y. Okay? What we don't yet have is y prime. So before we do any substituting, let's find y prime. So if y equals x squared e to the x minus 5x squared, we need to start off with the product rule. So y prime equals, well, the derivative of x squared e to the x will be first function, x squared, times the derivative of the second, derivative of e to the x is e to the x, plus the second function, e to the x, times the derivative of x squared, which is 2x. And then the derivative of negative 5x squared is negative 10x. So about as simply as we can write that derivative is like that. X squared e to the x plus 2x e to the x minus 10x. So here's what's going to happen next. There's the original y. We're going to replace it with that. There's the original y prime. We're going to replace it with that. Then see if we get a true statement. So let's rewrite our differential equation. So here's our check to see whether or not it's a solution. So we write x. Uh-oh, didn't want that. We write x. But instead of y prime, we put what we found y prime to equal, which is x squared e to the x plus 2x e to the x minus 10x. And then we write minus 2y. So we put minus 2, but instead of y, we put what we think y equals. X squared e to the x minus 5x squared. And then nothing else gets replaced. Equals. And then it got chopped off when I scanned it, but x cubed e to the x. So it's just a lot of algebra at this point to see if we can make the left side equal the right side. On the left side, distribute that x. So we'll get x cubed e to the x. Distribute the x to the middle term to get 2x squared e to the x. And distribute the x to the last term to get negative 10x squared. For the next parentheses, distribute the negative 2 to get negative 2x squared e to the x plus 10x squared. Yeah, then lots of cool stuff starts happening now. We've got a negative 10x squared and a positive 10x squared. We've got a positive 2x squared e to the x and a negative 2x squared e to the x. So all we have remaining on the left side is x cubed e to the x. All we have on the right side is x cubed e to the x. So is y equals x squared e to the x minus 5x squared a solution of this differential equation? Yes. And I don't know why I'm happier when the answer is yes, but I'm always happier when the answer is yes. It's like, yeah. Yeah, maybe that's what it is. So that's how we do that. All right, we can do that, can't we? Let's do another one. Number 14. Number 14 has slightly different directions. Determine whether the function is a solution of the differential equation. Now that y parentheses 4 thing, that means the fourth derivative. Doesn't mean y to the fourth. It means the fourth derivative. So the fourth derivative of y minus 16y equals 0. So again, I write my problem down a little bit differently than they do. I write the differential equation first. So the dE is the fourth derivative of y minus 16y equals 0. Our potential solution is y equals 3 times the cosine of 2x. Now, like we did on number 24, we're going to replace the original y with 3 times the cosine of 2x, but the work we've got to do is we've got to figure out what the fourth derivative of 3 times the cosine of 2x equals. It's not quite as bad as you think. Constant multiple rule. It'll be 3 times whatever the derivative of the cosine of 2x is. And the derivative of the cosine of u is negative sine of u times the derivative of u. So it'll be negative sine of 2x times the derivative of 2x. Then when we put all that together, that's a negative 6 sine of 2x, isn't it? Now take the derivative of that to get y double prime. Constant multiple rule again, so negative 6 times, and then the derivative of the sine of u is cosine u times the derivative of u. So that'll be the cosine of 2x times the derivative of 2x. And when we simplify that, we get negative 12 times the cosine of 2x. Take that derivative. Y'all still with me? Am I going too fast? All right, take the third derivative. Constant multiple rule again. That's negative 12. And then the derivative of the cosine of 2x is negative sine of 2x times the derivative of 2x. Now when we multiply all the constants together, we get a positive 24 sine of 2x. Take the derivative one more time. And we'll get 24 times the cosine of 2x times 2. So we get 48 times the cosine of 2x. So, in your original dE, replace the fourth derivative of y with 48 times the cosine of 2x. Replace y with 3 times the cosine of 2x. And then see if we get a true statement. And we do, because 48 times the cosine of 2x minus 48 times the cosine of 2x does, in fact, equal 0. Okay, so this determine whether the function is a solution, not all that bad, is it? You got to be good at basic derivatives, and you got to be good at basic algebra. I guess Algebra 1 students wouldn't call this basic algebra, but you get the idea. Basic for us. All right, now, number 5, different directions again. Verify the solution. So there is no possibility of getting a no. That is a solution. We have to just prove it. Okay? So for number 5, they give us, and I think they give this to us backwards. I want the dE first. So I want, in the second column, they give us that the differential equation for this problem is y double prime plus y equals 0. In the first column, they've given us the solution, which is y equals C1 cosine x plus C2 cosine x. Sine x. Who said cosine? All right. So, We know what to substitute in for y, but we don't yet know what to substitute in for y double prime. So let's get it. Let's get y prime. Constant multiple rule. The derivative of c1 cosine of x is c1 times the derivative of the cosine of x, which is negative sine of x. And then the derivative of c2 sine of x is c2 times the derivative of the sine of x, so c2 cosine x. And we can write it like that, right, with the negative in front of the c1. So I've got negative c1 sine of x plus c2 cosine of x. Take the derivative again to get y double prime. And see if you get what I got. All right, so let's do our check. Now, we know it's going to work. So if it doesn't end up making a true statement, we have made a mistake because it's a verify. So let's do our check. Replace y double prime with negative c1 cosine of x minus c2 sine of x plus replace y with c1 cosine of x plus c2 sine of x equals the right side of our DE 0. Well, yeah, negative c1 cosine of x and c1 cosine of x combine to give us a 0. Negative c2 sine of x combines with c2 sine of x to give us a 0. We have verified that that is in fact a solution. Okay, still doing okay? Now, number 11. So this time, verify the particular solution of the differential equation. All right, so here's the way that makes the most sense to me to write this down. Our DE is y prime equals negative 4xy. Our initial condition is that y of 0 equals 6. So whenever x equals 0, y will equal 6. And our solution, and it really is the solution because the directions say verify. Our solution is y equals 6e to the negative 2x squared. Okay, now, negative 2x squared. Let's find the derivative so we'll know what to replace y prime with. So y prime equals. Then I'm going to constant multiple rule this one. It'll be 6 times the derivative of e to the u. Derivative of e to the u is e to the u times the derivative of u. So e to the negative 2x squared times the derivative of negative 2x squared, which is negative 4x. So y prime is negative 24x e to the negative 2x squared. Okay? Now, there's a couple of different ways we can go about it from here. Here's what I think is the simplest way. We can verify this without using our initial condition. Okay? Like so. So here's our check. Replace y prime with negative 24x e to the negative 2x squared. On the right side, replace y with 6e to the negative 2x squared. Are the two sides equal? Yes. Now, why'd they give us an initial condition? Because all we've done so far is verified that it's a general solution. But that doesn't mean that we can get the correct particular solution. So since y of 0 equals 6, that means whenever x equals 0, y equals 6. So go to your solution, oops, and let's write that. So replace y with 6, and then replace x with 0. All right, now, one method for doing these is all we need, but I'll bet you can see what we could have done alternatively. Once we had this, all right, we need to take the derivative anyway, but we could put, could we? 0 there, 6 there. Yeah, but see, that would just be verifying that the initial condition made sense. I guess we do have to do it this way. So we've verified that the general solution makes sense, and then we verified the initial condition makes sense. I guess that is the way we have to do it. If they just make up the particular the initial conditions, it could be. But now it won't be because they've said verify. But they could give us the correct solution and then give us something weird like y of 0 equals 4 million, and that part wouldn't work out. Okay? But as long as they say verify, it's nothing weird like that's going to happen. All right. Number 28. Told you we were going to bounce around a little bit. All right, on 28. The directions say, some of the curves corresponding to different values of c in the general solution of the differential equation are given. Find the particular solution that passes through the point shown on the graph. So this sounds more like what we used to do, other than they're still giving us the solution, but in what we always used to do, they give us the little slope field, right? So we'd graph our own solutions, and then we'd do integration to find the actual solution. So this is closer to what we've done in the past, but they're still giving us the solution. So our differential equation is y prime minus 2x equals 0. Our solution, and in fact it's a general solution, is 2x squared minus y squared equals c. Now they even tell us that. By looking over here, they're telling us that whenever x equals 3, y equals 4, we can solve for c, can't we? So take your solution at the point 3, 4, replace x with 3, replace y with 4, and we can solve for c. So what does c equal? C equals 2. Can we, at this point, turn our general solution into the particular solution they told us to find? Yeah, all we got to do is replace c with 2. We never even used the differential equation. Okay. All righty. Here's your assignment. On page 409, do 1 through 5, 9 through 11, 13 through 16, 19, 20, 22, 24, 25 through 28, and 31 through 33.